Okay, folks, this is the tree breadth-first traversal explained with pseudocode. This can be applied to any language. I will be coding this in JavaScript later on in a different video. The goals of this video. So we're gonna go through definition, why we're gonna use it, and the strategy we're gonna use to build the pseudocode and ultimately the code. Breadth-first traversal, the definition is you start at the root, and then you go down a level, print children left to right, go down level, print children left to right, until, well, you have no children left and no levels left. And for this particular tree, go this way, 3, 18, 1, 4, 11, 30, 9 being first, of course, 9, 3, 18, 1, 4, 11, 30. So we know the definition of it. Why do we use breadth-first traversal? The reason we use breadth-first traversal is because our value might be close to the top. So, I mean, in this case, we don't really see a lot of savings, but let's say, you know, we had, oops. So we just had a tree that had a lot, it was very deep, many, many levels. And if we did a depth-first traversal, but somehow we knew that our value was closer to the top here, like 18, if it was depth, we'd have to go all the way down to the top, all the way down to the bottom, almost to the top, down to the bottom, almost to the top, hit the 9, down, and then we would eventually hit the 18. Okay, we don't want to do that. We don't want to do that. If we know it's close to the top, it's a breadth-first search. I'm sorry, breadth-first traversal. It's almost called like a near-the-top traversal. I don't know. All right, that is the why. Now the strategy. The strategy, okay, is if we print a 9, we want to come to the 3 and 18, and we want to get 3's children, right? 3's children. So they would go over here. And then we want to get 18's children. Go over here. All right, cool. So how can we do something like this? Let's build this up. So let's say you have your results, like a list, or you're printing out, and you have just a list of nodes encountered / the children of the nodes that you've encountered. So you encounter 9. 9 goes here. We have a 9. Okay, let's print the 9. Print it out. Okay, then we're done with the 9. 9 has children, 3 and 18, right? 3 and 18. Okay, let's say we print out the 3. Okay, see 3 has the children 1 and 4. We discovered them like this. 3 has 1 and 4. So before we come down to the 18 here, we're still dealing with the 3. So 3, did it have a left and a right? Yes, it did. So take that off. I'm going to have my 1 and my 4. So I'm going to take the 1 and the 4, put them down over here. 1, 4. Okay. Let's take the 18. Let's print out the 18. Does the 18 have a left and a right? Left or a right? Left and or a right? Okay, I see these two values here. I'm going to put them on the end. 11 and 30. All right. So now I get the 1. Put that here. Does 1 have left or right? No, it does not. 4. Does 4 have a left or right? It does not. 11. Does 11 have left or right? It does not. 30. Does 30 have left or right? No, it does not. But look what we got here. If you were pushing these results onto a list, you could then return the list, or you could print them out as they're coming in. To this data. You could print them out, you could put them in a list, you could do both, and then return the list.